I think then we will just start this event. So I'd like to, it's 10 o'clock and we're very precise in drilling. So we'll start and I'll chit chat for a little while so that the rest of the 129 signups can have some buffer time to join us. For your awareness, we'll start recording in a minute's time. So this meeting will be recorded. So it's also available at a later stage. And I believe that Lynn also will send out a little questionnaire after this session. Right, Lynn?
Yes, that is correct. And the recording has started as well.
The recording has started. And today we have a very interesting topic. And we're going to start off with Adriano Massini from University of Oslo to talk about natural methane seepage. And then there will be a little chicken and egg investigation from Stig Morten Knudsen on the relationship between leakage from wells and natural seeps. And then finally, Stefan Polto from Institute for Energiteknikk will present a proposal for building knowledge around this. So with that, I leave the word to Adriano and best of luck. It's good if you unmute.
Am I?
Yeah, now you're good to go.
All right. Can you all see me? My screen?
Yes.
Okay. Then thank you everybody for joining. I will today give a brief overview about geological methane seepage, and I will take you over a short trip over several localities where this type of phenomenon occurs. Methane is a greenhouse gas, is 28 times more powerful than CO2 over a 100-year time horizon. It is released by natural and anthropogenic sources, and about 1/3 of the 560 teragram per year is released, is essentially fossil methane, released by fugitive emissions and oil and gas extraction, distribution, and coal mining. About 45 teragrams per year, and this value is largely underestimated in my opinion, is naturally emitted through Earth's degassing, occurs through seeps, mud volcanoes, and diffused microseepage, typically in petroleum sedimentary basins and geothermal areas. And these are the main players that we will look at today. There have been identified about 76 big emitters, meaning that these big emitters released more than 10 to the 4th tons per year of methane on the atmosphere. And these are mostly mud volcanoes. These are some examples. They are kilometers in size with a kilometer-sized crater at which we have invisible microseepage through microfractures, through seeps, diffuse seeps, or gryphons like this one we observe in the central area of the crater. And of course, these structures, they erupt periodically every few years or so, depending on how long it takes to build up the overpressure to contrast the overburden on the top, and they release huge amount of methanes for a few days. And this methane can self-ignite also, resulting in these spectacular mud eruptions. Another big player that I'm sure will become more popular are the hybrid systems. These are essentially halfway between the purely magmatic systems and the purely sedimentary system like mud volcanoes. And I'll show you an example here of the Lucy eruption in Indonesia that I started since 2006 when it started. You see the magmatic complex is about 10 kilometers away from Lucy here. And if we look at how it looks in the subsurface, we did the tomography and we showed that we have the magma chamber just below the volcanic complex. And we have an intrusion, magma intrusion, following a fault plane into the sedimentary basin, essentially baking all the organics that we have in the source rocks in the area, creating large amount of overpressure and resulting in a vertical conduit that manifests at the surface as Lucy, where we have two large vents about 100 meters in diameter in the central part, releasing CO2 and methane. I'll show you now a short movie that AGU did. They did a special coverage on one of my articles, just to give you an idea how it looks like. Quickly, the eruption started. It was actually 10 of eruptions aligned along a 1 kilometer length alignment, and it covered very quickly several square kilometers of area. Today is about 7 square kilometers of mud covered area. 60,000 people had to be evacuated, literally swallowed the whole city. We had a geysering behavior and with pulsating behavior at the crater size. And as I said, our tomography studies showed that the volcanic arc, which is just behind, 10 kilometers behind, created this overpressure in the subsurface. And a few days after, actually less than 2 days after a major earthquake that was in the island, this overpressure was released at the surface, resulting in what we see today at Lucy. So we were able to quantify how much methane and how much CO2 comes out from this after several years of study. And we figured out that we have three main players that release gas. If we take this is a satellite view, if we take a profile from left to right, crossing the main vents that you see here on the left, we have most of the emissions are released by the two vents. We have 200 meters diameter vents. We have a system of seeps that are surrounding a region of 7 square kilometers. All these red ones are seeps. We have thousands of them. And then we have the gas that is released by invisible micro seepage through a vast area of 7 square kilometers. So we quantify that in the terms of 0.1 teragrams per year is the largest emission of methane. If you think in perspective of a global accounting, this is quite a lot. If we move to offshore degassing site, the discovery and the studies of offshore degassing intensified since the 80s. We have 4 main players for degassing. We have the cold seeps. These are essentially seepage sites of hydrocarbon-rich fluids released on a focused locality. We may have pockmarks. These are circular depressions. They are related to the seepage of fluids from deeper-rooted conduits that may bring in suspension the fine-grained material, and then the system is sagging. So we have these circular depressions at the surface. We may have also mud volcanoes offshore. We have one, in fact, offshore Norway here. These are large structures. They are positive structures where we have, if you've seen the eruption of sediments and fluids, or we may have the seep mounds. Seep mounds are positive features consisting of carbonate buildups, and we'll see in a second where these carbonates come from. The main let's say, features that we observe at seepage sites are obviously the methane seepage released through bubbles that we observe on the seafloor. We may have microbial mats on the surface, on the seafloor and in the subsurface. We typically have chemosymbiotic fauna living in symbiosis at these seepage sites, several types of fauna. We may have the altigenic carbonate precipitation. This is very typical at seepage sites. These are essentially the bioproducts of the consortia of archaea and bacteria that live on the seafloor. They cooperate oxidizing the methane and reducing the sulfates. They produce CO2 that bonds essentially with the calcium ions in the water column and precipitate as carbonates. We may have gas hydrates if the pressure and temperature conditions are favorable. And we may have also oil seepage at these sites if the seepage plumbing system is tipping from deeper sited reservoirs. how do we investigate these seepage sites? Well, typical geophysical investigation through multi-beam, side-scan sonar, seismic, 3D seismics to understand the subsurface plumbing system and to identify the right positions where we have the major seepage sites. At these sites, we may position landers to do multi-parameters monitoring. We can visit them with the ROVs to collect samples of gas and sediments. And this provides important information about the mechanisms at the sites. If we may have deep thermogenic gas, shallow microbial gas, or a mix of the two. If we have, for example, gas hydrates. And even at sites where we don't see the bubbling, like in this one, we can study the microbial colonies. If we see presence of bacteria and archaea, we know that this is a methane site. Water geochemistry, also very important, extracted from the sediments. It may indicate us presence of water released from the clay mineral dehydration, gas hydrate dissociation, brines, or phreatic. And very important, I think, is the study of these carbonates. They are literally archives of information for us. They can be dated with uranium thorium, and so we can know at the timing of the seepage of these sites. And we may also, studying the fluid inclusions inside the crystals, we may understand the composition of the fluids at the time of the seepage. We can study them through microthermometry or Raman spectroscopy. You see a small fluid inclusion here. So it gives insights about the ancient and modern migration. If we look at our coast here, offshore Norway, here you have all the wells in black, but we have many major Pockmark fields, which I framed here in red, and they extend over large area, even further north in the Barents Sea, where we have evidence of ancient and modern degassing. Interestingly enough, the southernmost Pockmark fields are less or not active, while the further north we move, we have stronger activity of these sites. I will show you an examples of the Troll field. I'm sure you all know it. It's a large concrete gravity-based structure positioned in the Norwegian Channel. And what was observed in the past is that they had to blade off routinely the well annually in foundations, skirt compartments, as you see here. And that started to raise question, what were the causes of this high pressure? And if this was causing a potential hazard for the structure. So I started the search for evidence of potential active fluid seepage at the Pockmarks and understanding the origin of this gas. So you see here the multi-beam image, and we identified about 7,000 Pockmarks around the field, over a 600 square kilometers area. More than 300,000 Pockmarks are expected if we extend this survey. And there is no evidence of structural control on the position of the Pockmarks. And there is no evidence of any activity of these Pockmarks, so based on samples of sediments. But what we could figure out studying the carbonates and dating them, we observed that their age is 9.6 thousand years, which coincides with the end of the last glacial, when the pressure and conditions changed during the gas retreat, favoring the formation of methane, which was released by the dissociation of the gas hydrates. And for the record, the gas that is observed around the platform today is actually shallow microbial gas, which is locally produced, so it doesn't represent any harm. If we move even further north, and now here we are in the Niega field. It's located just to the north of the Storegas light that you see here in the figure. And here we have the classical, all the classical, let's say, ingredients that we have at active seepage sites. We have the gas hydrates, we have the methanogenic carbonates, we have the chemosymbiotic fauna. If we move even further north, we go to the Barents Sea. We have both evidence of ancient and active degassing. Here you see a model that was proposed for the activity of these huge Pockmarks present in the Barents Sea. It's very similar model to the one that I showed you for the Troll Pockmark field. During the last deglaciations, the ice retreat changed dramatically the pressure and temperature conditions, allowing the thawing and the dissociation of a large amount of gas hydrates, resulting in the sudden gas release at the surface. And today, this gas seepage is still active at these pingos around and inside the Pockmarks that we observe with these gas flares in the water column. So if we want to look at this from a perspective of water column and climate implications, so we know that the gas hydrate dissociation has been invoked in the past as one of the factors that may have contributed to the PTM when large amounts of greenhouse gas was released in the atmosphere. And from a modern perspective, previous studies show that if the seeping methane gets oxidized in the water column, if our seepage is located at water depth higher than 150 meters. So in principle, this shouldn't represent any harm and shouldn't have any impact for the atmosphere. However, have you seen in this movie here on the side, we have plumes in the water column that are more than almost 1 kilometer tall. So this assumption is not always valid. Depending on the sites, we may also have an implication for the methane release in the atmosphere. But also, what we want to investigate is what is the impact of this methane in the water column, these huge flares that we have. It's very important to quantify and model the methane budget that is released by this methane seeps from the seafloor. And ultimately, we should also focus, I think, on the influence on ocean acidification and oxygen loss that we have in the water column, how this may influence the ecology in the water column and at the seafloor, and if this could eventually even influence the movement of water masses and in turn have impact on local and global climate. And finally, I want to give a short slide about leaking wells. This is an example of a flare observed above the Whistling Central gas field. Is this a leaking well? Is this close to the well? Do we have any direct evidence of wells in general leaking? This could be also new or old seepage sites. That's why the carbonates that we observe at this seepage site would be very useful to understand if these are modern or ancient sites that existed before. And then finally, the question if the wells do affect deep or shallow fluid migration pathways, and hence for migration of deep thermogenic or shallow microbial gas. So I'll leave you with the conclusions. As we have seen, methane seepage is a broadly distributed phenomenon on the planet in time and space. In the Norwegian Channel, only about 1 million Pockmarks are expected to be there. The seepage site investigation reveal insights about the source of the fluids, shallow or deep, and the tempo of this seepage. The pathways for fluid seepage may be controlled by tectonic discontinuities or can be randomly distributed in case of a rapid gas hydrate dissociation over huge areas. And we have indeed the paucity in quantifications of the currently released gas, and this may have also impact on our future climate. And ultimately, what is the potential influence of borers in fluid degassing at the seafloor? This is a question that we aim to investigate. And with that, I thank you for your attention.
Thank you very much, Adriano. That was very interesting. And I know that for your next field trip, I'll join you on the mud volcano sites. It looks really thrilling.
We have a summer school, actually, every year in Azerbaijan, if anyone is interested.
Moving on to this chicken and egg investigation that Stig Morten Knudsen will take us through on the relationship between leakage from wells and natural seeps. So the floor is yours, Stig Morten.
Thank you. Can you see my slide?
Yes, we see it.
And you can also see my pointer?
No.
No? Okay, that's interesting. Okay, let's see if I can do this then. Okay, I'll try to talk without my pointer. Okay, so my name is Stig Morten Knudsen, and I'm giving this talk on behalf of my colleague Rune Mattingsdal and myself, and we are both with the NPD in our offices in Harstad. And I guess the title is a little bit not clear, but I'm going to get to the point with the title in the end. And the title is, what actually is the reason for many of these leaks that Adriano talked about from wells or close to wells, and how important are the natural leaks, especially in the Barents Sea? So that's where we're going to go. So the contents of my talk is I'm going to give a little bit of background for this, should I say, renewed interest in leakage from the NCS and from the seabed in general. I'm going to talk a little bit about geological settings and seepage, mainly in the Barents Sea. And I'm also going to show you some examples that we have just done together with CGG on oil seepages in the Barents Sea. And then I'm going to go to the southern part of the Barents Sea and show you some examples of gas seepage from well and from fields and close to wells, but not necessarily from the wells. And then I'm going to talk briefly about that chicken and egg thing and talk about some implications and relations of wells versus the gas seepage. Then I'm going to give you some preliminary conclusions. So last summer, as I said, one of the things that really spurred this renewed interest in leakage from the continental shelf or from the seabed was what you see on the left-hand side of this slide. And that was when Greenpeace went down to an old borehole on the UK side in the North Sea and saw and took a movie. That's not a movie that you see, that's obviously a still photo, but they did see that there was a lot of methane leaking out from the well called UK 224B. And that was a well that was drilled in 1990 by Mobil North Sea, which is now part of ExxonMobil. That spurred a lot of interest. It even spurred so much interest that it went all the way to the Norwegian Parliament. And that's what you see on your right-hand side. And I'm sorry for your English-speaking parts of the audience, but that's what it really is. And those that are Norwegian can read it. It's really a question from one of the members of the Parliament to one of the ministers. And he's really asking, what do we do, or what do the authorities do in terms of mapping methane leaks from the NCS? And are we doing anything? And as Adriano showed you, we are doing something. And I guess the question also is, are we doing enough? And I guess maybe that's something we can discuss by the end of this seminar today. So if you look at the Norwegian Continental Shelf, and the map to your left-hand side is the NCS. And for those of you that are familiar with the NCS, you know that the green areas is the ones that are open for exploration. And the ones that almost doesn't have a color but are still on the NCS, those are not open for exploration. And again, I'm sorry for a lot of this being in Norwegian, but all these stars are some of the known leakages that we see from the shelf. Some, as you can see, are related to discoveries or to wells, but some, especially in the Barents Sea North, the Storbanken and the Hopenjup and so on, are not related to any wells. They are natural seeps. And on your right-hand side, you see some of the many seeps that we have documented in the Barents Sea. And again, I'm sorry for being in Norwegian, but if you want to check out all these different reports and articles, you can do that later on, I guess. And also, what I think is important is to be aware of is that the Barents Sea probably has thousands of documented national gas seeps. Thousands, there are many of them, and most of them are not related to drilling or not related to hydrocarbon or petroleum activities. So what I'm going to do now, I'm going to show you 2-3 examples. I'm going to show you one from the Storfjordrenga Pingo, or actually, I think Adriano showed you a picture of it, but I'm going to illustrate that, what it actually looks like from the seabed up here. Then I'm going to go to Storbanken, and then I'm going to go down to Lopphøgda or the Bjørnmeran platform and further down to the Goliath as examples. So is that movie running or?
Yeah,
excellent. So then we can enjoy the soda pop factory. That is from the Storfjordene gas hydrate mounts. And it's situated, it's really hard to see, but if you look on the top of that movie picture, so it's about 376 meters depth. And it was recorded by CAGE, the Center for Arctic Gas Hydrate Environment and Climate in Tromsø. I think it was in 2018. So that's what a natural seeps looks like in Storfjordene. And if you look on the right-hand side, that is a picture or an illustration of these pingos, or these mounts. And I think also Adriano showed you this picture where we see these gas flares coming out. So if you send an ROV down, this is what the gas flares would look like on the seabed. And the way of registering these leaks is also what Adriano touched into. It's either by hydroacoustic or multi-beam, as you see on your lower right-hand side. That's just an illustration from Mariano, where you sort of survey the sea column, and you can see these seeps coming up. That's the usual or obviously easiest way to do it. If you want to be more concrete and precise, you can go down with an ROV and you can take a movie, or you can even take samples. That's also where we touched upon earlier on. So that's what it looks like in real life, to put it that way. So now I'm going to show you some seismic, and this is a seismic profile which we published in 2017, or part of our work in 2017, when we did the resource estimation of petroleum resources in the Barents Sea North. And if you look first of all on your index map on your lower right-hand side, you will see where the white line where the profile goes. It goes from the Olga Basin to the southeast and all the way up to Kong Karls platform, just east of Svalbard to the northwest. And I'm sorry there's not a horizontal scale, but that total length of the profile will be about 350 kilometers. And what is dominating the setting or geological setting in this profile are these huge clinoforms indicated by these orange dipping reflections coming in from southeast to the west and filling in the Barents Shelf during the Triassic, and then you see the Jurassic on top. And you see the feature, the Storbanken high, and you also see the Kong Karls platform, and you see these nice structures on the Triassic and the Jurassic level in these areas. That structural map that is used as a base map on your lower left-hand side again is close to the top Jurassic horizon. And what we also know is that in front of these clinoforms, the Triassic clinoforms, we know that we have well-developed source rocks. Some call it steinkobbe, some call it bottenheia, some call it something in between, and we can discuss the age of it, but that's not the purpose of today's talk. But we also know that these source rocks in the Barents Sea and also in the Barents Sea North has generated oil and gas. And what we also see, and that gets back to today's theme, we also see that these gas generated, they actually migrate up and it comes up to the seabed, shown with these red things on top of the profile as leakages or as natural seeps into the water column. And if you do a close-up of the Storbanken high, it will look something like this. So this is a completely different scale. This is a shallow seismic. It goes down to about only 500 milliseconds. It goes from north to south, and there is a scale showing it's just 1 kilometer to your lower left. And you then can see these gas flares that comes up on the top of the Storbanken area. And we also see that these gas flares in the subsurface are linked to bright spots in the upper Triassic and the Jurassic stratigraphy. So for us in the NPD, which really are to focus on resources and petroleum system, this is really interesting and tells us a lot about the history and about the resource evaluation in these areas. But it's not only gas that comes up, and we have started to investigate oil seeps in the northern Barents Sea. And on the map on your left-hand side, you will see Edgeøya, and you will see Nordøstlandet, and you can also see Kong Karlsland, Bjørnøya, and Hopen on the left-hand side of that map. So that is actually a map of the northern Barents Sea with a lot of colored dots. And the colored dots are where we, together with CGG last year, indicated potential oil seeps on the surface, where we use, as you can see on the right-hand side of the slide, satellite data to try to monitor and to try to detect seeps on the sea surface. And the different colors on the different blobs are actually what type of confidence we have in these seeps being real or being ships or whatever they could be. And I'm going to show you some examples of something that really had high confidence. And that is, again, you can see from the yellow circle, those are very high confident seeps that were indicated by CGG last year. And what we did on your right-hand side of the slide is that we went back to older public satellite data, which is out there. You have to dig a bit, and you will probably have to have huge machines or at least storage capacity to find it and to use it. But if you do, you will actually see that as the slide shows, that if you go back in time, and we've done it from 2017 on up until today, you will see that these slicks or these leakages of oil from the subsurface is fairly constant through time, at least the last 4, 5, 6 years. There is a scale on that uppermost right-hand side, and that little scale is hard to read, but that's about 5 kilometers. So you can see that these slicks that is on the sea surface, they are fairly significant and they are stable through time. So that also, of course, gives us some indications of what could be happening in the subsurface, both in terms of petroleum systems, but also in terms of leakage of whatever comes up from the seabed and into the water column. So that was a little bit about Barents Sea North. The Barents Sea North is not open for exploration. Now I'm going to move to the Barents Sea South, which is open for exploration. I'm going to show you some examples that we acquired together with Cage last year. And this map that you see on your left-hand side, probably most of you are aware of what it is. It's the license map, the NPD license map, which we usually put out from the Barents Sea. The different colors represent the different equity stakeholders in the different areas. And you also see the APA red box, as you can see it. So for those of you that are sort of very known up here, Snøhvit is in the middle of the Hammerfest Basin. I can't point, I forgot that. But the dark or the black lines that you see is that cruise that we did together with Cage last year. And all the stars, the yellow stars that you see along that cruise is where we detected flares from the seabed. And what you can see is that there are some flares that are related to fields, Goliath to the south. There are some that are related to discoveries, Kaurus, Longletin. And I think also if you went further north, which is unfortunately out of this picture, if you go to Wisting, you will also see there are some flares related to Wisting. And I think Adriano touched upon that. So what we see, and that's what it says on the right-hand side of this slide, is that there are several shallow seismic gas anomalies associated with these wells and fields, because we have tried to systematize. Do we have any anomalies in the subsurface, the shallow part of the subsurface? And does these ones relate to the flares or to the leakages we see? And what it also says in the middle there is that most of the wells or the fields with seismic anomalies are also associated with gas seepages. That's about 30 of the leaks that you see, those yellow stars on the figure. And of the 17 surveyed wells, about 9 of them, or 53%, showed indications of leakage. So let's have a look upon a few of them. And I'm going to start with Longletin and Kaurus, and then I'm going to go down to Goliath. So this is on your left-hand side. You will see the Kaurus discovery. I think it was made in 2008, and I'm going to just click this one as well. And that was a discovery of gas in the Snod reservoirs. But what we also see is, can I go one back? Yeah, if you look upon the shallow parts above the Kaurus, there's a lot of high amplitude anomalies. And on that seabed, you can see that we also saw that there were gas flares associated with the shallow anomalies. That's the black thing sticking up into the water column on the top of the profile. If you go to the northeastern part of the slide, you also see Langlitin, where we actually crossed straight over the well. I think it was really in 2013 or 14 or something like that. That was also a discovery, but down in Kobbe. And we did see some leak along that well. But you also saw some leak just outside the well, as you can see, which is, it's really hard to see from this, but you can actually observe a very nice polar reversal on the very shallow parts of the subsurface. And you can see some shallower anomalies, suggesting that there very likely is gas in the subsurface coming up at Langlitin, but also on the sides of the well pad, indeed. So if you go down to Goliath, this is what it looks like. This line goes from east-southeast to your right and up to west-southwest to your left. And it shows wells 71, 22, 76. And for those of you that are familiar with Goliath, you will see that the top of the structure is at about 1200 milliseconds. And then the base tertiary will be at about 750. That's the high amplitude, 750 milliseconds. And then we have the Uru, or the glacial sediments, from about 500-600 milliseconds and up to seabed. And from this well, we also saw some leakage when we crossed it with the multi-beam data. And that's what it's indicated with this black line going into the water column. But if you go to a different location on the Goliath structure, and again, the Goliath structure on this profile going north to south is at about, if I can see, about 1000 milliseconds. So that's the structure on the realgrund level. But you see, if you go further up to the base tertiary, about 700 milliseconds, but also to the glaciogenic sediments at about 500-600 milliseconds, you see high amplitude anomalies, and you see leakages related possibly to these high amplitude anomalies and into the water column. And this is not close to any wells. This is natural leaks from the Goliath field. So then I'm going to present to you a few models for this. And this is sort of, this could have been Goliath, or it could have been something else. But what we do see, if you make a sketch drawing, we make one drawing where we have the sea surface on top. We have the water column, then we have the seabed, the glacial-marine units, and the sedimentary rocks, which I have tried to indicate on the left-hand side of the figure. And then in depth, in big red, we could have a gas or oil accumulation. And some of these might, through time, leak into the shallower overburden. And they might be stopped, and then you have a shallow gas along in the Barents Sea, very often along Uru or close to the Uru, the glacial sediments. And some of them, again, are leaking into the water column, as we have seen. And then comes the big question, of course, what happens if you put a well through this, either through the anomaly or just into the system as such? Does this mean, and that's, I guess, our question, if you look at the size of that gas seepage red thing on the top in the water column, we have tried to indicate that with the size of it. Does this mean that a well, which then cause some more leakage, does that just mean that the natural leaks go down? Because what you actually see is that the new path where the gas could come up, just find a new way, a new vent, and that actually is decreasing the natural seep that was there in the beginning. So that's a hypothesis that we have. What does actually the exploration wells or production wells means if they go down into a system like we see on the screen right now? And of course, the crucial thing is, and that implies back to what Adriano said, both in terms of volume and climate and so, is the output or the volume of gas seepage unaltered by drilling, or does what we do as humans influence this seepage from the subsurface?
You have one more minute.
Yep, I'm going to wrap up. I'm just going to show you now what we are doing in the NPD. So this map on your left-hand side is a busy map. Again, it's a structural map of the Barents Sea. And all those lines that you see, those wiggly lines, those are the cage surveys. And the squares that you see, especially on the right-hand side, is the Mariano data sets. So we have started to investigate for all the wells and started to map out the distance from the wells to the anomaly to see if you can find any relationship between anomalies, wells, and leakages. So, the conclusions. We believe that the water column data adds to the understanding of the petroleum systems. We already know that there are thousands of natural gas seepages from the Barents Sea, and we have also now started to document the natural oil seeps. We also see that there is a strong linkage between the nature of the subsurface and the observed seepages. And also definitely there is a link between shallow seismic anomalies and seepages. The relationship between natural seepage and well-induced seepage, as we call it, that is still a little bit unclear, both in terms of volume implications, and that comes back to my chicken and egg. What actually did come first, the leakage or the well? And with that, I just want to round up with some acknowledgements of all these cruises we've been on, mainly my colleague Rune Mottingsdal, and thank you all for your attention.
Thank you very much, Stig Morten. Since I'm joining Azerbaijan trip with Adriano, I'll probably join a cruise in the Barents Sea with you, and then I will give the word to Stefan to take us through a project proposal for building knowledge on this.
Yes, thank you. Can you hear me? I am on full screen now and see. Yes. Can you hear me?
We can hear you, yes.
Okay, good. Sorry. So thank you for staying tuned in, and thank you to the FORCE committee for organizing this webinar. So this talk is about presenting a proposal for a knowledge building project for the industry. And knowledge building projects are usually referred to as a KPN. So they're research projects that should contribute to the long-term development of competences by training researchers, such as PhDs and postdocs, on themes that are important to the industry. So in this KPN project, we have a consortium of 4 research organizations with IFE, the Institute of Energy Technology, as a project owner, and we have the University of Tromsø, the University of Oslo, and the University of Stavanger as research partners. So in this consortium now, we need to find a minimum of 2 industry partners, which is the aim of this talk, is to reach out to potential industry partners. And here I'm going to try to convince you to join this project by presenting what we are planning to do and what we want to achieve. So the project mission is fairly simple, is to understand the fate of plugged wells to improve the abandonment procedures of tomorrow. The project is relevant to the UN Sustainable Goals 9, 13, and 14, and also relevant to the United Nations Decade of Ocean Science for Sustainable Development. So like in the previous 2 talks, we heard that natural seepage is a fairly common phenomenon that allows deep fluids to be released at the surface. But we don't know how the dynamics of natural seep system change after we plug and abandon a well. And as Stig Morten said, and also Adriano, some of the wells are associated with acoustic anomalies, which indicates that some gas is seeping out from the subsurface near the wellhead. However, we don't know how much gas is coming out. We don't know the source of the gas, if it's shallow or deep. We don't know if the seeps would, if the acoustic anomalies are related to natural seeps that would be present regardless if the well was here or not. And we don't know if the well path is actually draining all the fluids that would have otherwise naturally seeped. And to understand this is basically boils down to understanding the natural fluid migration and seepage near wellbore path. What is the influence of the wellbore path? And this is very important because we have several thousands of wells in our backyard, over 7,000 just on the NCS, and every single one of them will have to be plugged and abandoned. And like Stig Morten showed, I have the movie. This is Greenpeace released this. It's supposed to be near a wellhead. What I found, it's the result of a shallow gas blowout during drilling. So I don't think there is any wellhead. It's been leaking for 30 years. It's biogenic gas. And the problem with Greenpeace is that they don't provide any information. So like the typical ROV videos, you have coordinates, depth information. They also don't release cruise reports. So you don't know the activities, what they did over at this site, if they collected some of the gas, or if they collected some of the shells, or if they collected any other type of data for that matter, except that video that chose to release to the media to try sway public opinion the way they wanted. So anyway, for us, how we're going to do things is we want to do a multidisciplinary data acquisition using the research vessel Crown Prince Haakon, which is the latest research vessel that is equipped with the latest high-tech instruments, and also has 15 laboratories on board. And with it, we can acquire high-resolution 3D seismic over areas that we select and that contain abandoned wells. And to that matter, we'll use the P-cable system that is part of the national infrastructure at the University of Oslo. And because the Crown Prince Haakon has a dynamic positioning, we can deploy the ROV, remotely operated vehicles, to collect sediment samples and gas using the robotic arm. The ROVs also can be used to acquire high-resolution bathymetry and do video surveys by flying very close to the seafloor. Also, because the Crown Prince Haakon, with this dynamic positioning, we can deploy seabed observatory like the K-lander over periods of days to weeks to monitor seepage and measure ocean parameters. So our plan is to combine all the geophysical data into an integrated 3D model of the subsurface, the seafloor, and the water column. And this data cube will be used to interpret the geological structure, image the fluid migration pathways, and identify the exact location of where fluids are actively seeping, which would be at the roots of the gas flares here in the Pockmarks on the seafloor. So with this 3D model, we also want to integrate other types of data, mainly environmental and geochemical. So this 3D model will be used as a framework or as a matrix, so to speak, to graft on it any other kind of data. With the ROV, we can go down to the seafloor and do a visual characterization of the environmental condition. We can pick up, collect some shell fragments, some carbonate crust, or we can also collect some of the gas. We'll have an extensive analytical program, but mostly what we want to do is fingerprint the source of the fluids by using isotope geochemistry, that also all the gas samples and the carbonate crust and shells will be analyzed at the IFE Geochemistry laboratory to determine if the fluids are deep or shallow, or if the carbonates are related to seepage activity. And if they are related to seepage activity, we can then, like Adriano mentioned, date them using uranium-thorium method that we will do at the IFE Geochemical Laboratory. So we can fingerprint the source of the fluid and date the onset of seepage. Regarding the water column data, for this we will deploy in strategic location, like near gas flares, where we identify gas bubbles, these seabed landers, to measure the flux of methane that are seeping out of the subsurface, and also monitor the variation in seepage intensity over periods of days to weeks, and possibly correlate these changes to variation in ocean parameters such as tides or currents or temperature. One of the aspects of the work is also to quantify the environmental impact of the seepage. And for this, we need to identify the end station of the compounds that are seeping. So where do they end up? And for example, for methane, we want to know how much of the gas will be dissolved into the ocean to contribute to ocean acidification, how much of the methane will be released into the atmosphere to contribute to global warming, and how much will be consumed by the chemosymbiotic organisms to sustain food web and in the end fish stock. So in the end, not everything is negative about seepage. We also plan to benchmark our observations and results that are collected near abandoned wells to a natural seep that is away from any borehole. And for this, we plan to use the EMAN7 project, which is part of the phase 2 of the Lofoten Vesterålen Ocean Observatory and focuses on the node 7 in the Hola Trough. So the node 7 is a permanent seabed observatory that is connected to a land station for power and data transfer. So is actually online now and is located next to a site that is experiencing active methane seepage. For the modeling, we want to use the results and interpretation to constrain numerical models to evaluate the effects of abandoned wells on the natural fluid migration. So we want to use the numerical models to predict where and if leakage will occur and also test some of our hypotheses. We've done modeling of fluid migration through geological structures before, but we haven't yet coupled the geochemical processes and fluid flow. So that will be something interesting to do. And the result of all the project is to come up with recommendation to improve the strategy for abandonment of plugged wells. So it's including the design of plug and determine most suited type of cement. And the results are also relevant for the reuse of depleted reservoir for storage of carbon or hydrogen or geothermal energy. In summary, the project fate of plugged wells after abandonment, we want to acquire, analyze and interpret subsurface seafloor and water column data and integrate it into a 3D model. We want to understand how the regional fluid flow is influenced by abandoned wells, and we want to quantify the environmental impact of seepage in terms of ocean acidification, climate change, and on food web, so ecosystem impact, and do a recommendation on procedure for future well abandonment. So the budget here, it's a 3-year project. We estimated 25 million kroner. We budgeted for 3 PhDs and 1 postdoc and a 2-week survey on board the Crown Prince Haakon with the ROV and the seismic acquisition and seabed lander. So we're looking for about a contribution of 5 million kroner from industry partners. So it's 20% of the total budget. The remaining 80% should be covered by the Norwegian Research Council if the project is granted. The deadline for proposal submission is February 2022. We have some time, but not so much. And the added value of being a partner with us is that you will have access to the collected data and interpretation. You will be able to influence the direction of research, propose a potential study area. In the end, we will write great high-impact scientific papers. You'll be able to optimize plug and abandonment procedures, and it's also about improving public confidence in offshore drilling activity to take back the control of the narrative in the media that you like Stig Morten said, can reach government and change policies. So this is my last slide. This is just an overview of all the work packages for the project. You're welcome to take a screenshot. There is my email address, so you are welcome to contact me for further detail or have a meeting with the other research partners. And with that, if you have any question, I'm here. Thank you.
Thank you very much, Stefan. So that concludes the three presentations, and there has been a couple of questions. I'll go through them. The first question was from Per Christian Munkerud, who asked, is there a requirement to run and cement casing through shallow gas that will eliminate seepage? Absolutely, there is. So I think I can answer that. But the John Underhill question for Adriano, I'll leave to Adriano to respond to. What role did the drilling of an exploration well have in triggering the Lucy mud flow by providing a well pathway for pressure release and mud escape? Adriano, can you comment on that?
Yes, I don't know if you can you hear me?
Yes.
Yes, to answer, John, I mean, this is an old debate. I mean, there is several evidences that show that most likely the well was not controlling this. I mean, the fact is that the initial eruption site was more than a kilometer away from the well, together with about 10 more eruption sites that were distributed along a more than 1 kilometer long alignment, which coincides with the fault. Even Lucy today is more than 200 meters away from the original position of the well. The eruption of the fluids at Lucy are coming from are mantle-derived fluids coming from more than 5 kilometers depth. The well stopped the drilling at 2.8 kilometers, so should have drilled much deeper to tap from the origin. So it's not exactly the same example that we see in Goliath. It's a much deeper system. So we either invoke that the drilling could have triggered the activation of a fault, because we know that the fault was reactivated with the cracks and fractures and distribution of all these seeps, or otherwise it's difficult to explain. Also, the drilling data, they have been explained in different manners by different teams. I didn't go into the drilling data, but I stick to the facts. I see fault reactivation, distribution of the things, deep fluids. I mean, even if you see the seismic data before the eruption site, you can see the overpressured area at depth that forms this kind of diapir. So difficult, I think this it's difficult to answer, but based on the evidence, scientific evidence that I have, I don't see this drilling scenario, which is depicted by many as a realistic.
Thank you for that answer, and we'll leave it there. There is one more question, and I realized that we're very close to lunch and the end of the meeting. But Jens Martin Wied has the question: if Pockmarks can Pockmarks observed on overburden horizons be related to hydrocarbon leakage from an accumulation below? And how do characteristics of Pockmarks related to water and gas differ? Anybody that wants to have a comment on that?
Stig Morten, I can try. I guess they could be related. It is always easy to differentiate between water coming up or gas or both, and very often it could be both. So I guess it's always almost the same as Adriano just said. We don't think it is. We're not sure, but we think it is this way or that way. So there's a lot of uncertainties in what actually causes the pockmarks. And there's another factor with the pockmarks, and that is how old are they? And I think we also touched upon that. How can you age date the subsurface or the substrate, sorry, in the pockmarks, which I think will be important.
Okay, thank you for that, Stig Morten. Last question before we say thank you to the presenters and hang up. That's any seabed hydrate studies for climate or resource harvesting that are planned and ongoing? I guess this one is for you, Stefan.
I know Adriano is. You're talking about hydrate for impact on the climate.
I guess so. This is Tor Allan Garden who has asked the question.
Well, there's been in the news of this that okay, is it climate change that is triggering the dissociation of gas hydrate, or is it the other way? And again, like Adriano, if it's offshore, how we don't know if the methane is reaching the atmosphere, so we don't know how, and we don't know if the methane that is dissolved in the ocean, how does it react to the ocean, because it's causing ocean acidification and slowing down of the ocean currents to equilibrate the properties of the ocean to absorb the heat.
Yeah, I guess the question is are you aware of any studies ongoing or planned regarding this just now?
No, I don't. No, I'm not aware.
Okay.
Sorry, then I was totally off.
No problem. With that, I just want to say thank you to Stig Morten, Adriano, and Stefan for their very good presentations. And I see there still are questions, but I'm merciless with respect to time. So we are 1 minute over 11. So we'll cut the lines here, and it's up to you, Stefan and Stig Morten and Adriano, if you want to read through the meeting chat and answer. That would be nice of you if you could. So thank you all for attending. Also, we had close to 100 attendees, so I think it was worthwhile for all of us. A good, well spent 1 hour, and have a nice weekend.